Indeterminate forms and L'Hopital's rule. So here, goals: understand how to use L'Hopital's rule to find limits of certain indeterminate forms. We'll see what those are here in a second. Be able to adjust other indeterminate forms so that you can use L'Hopital's rule. So we'll see there's two forms basically that L'Hopital's rule is used for and really designed for, and then there's some other forms that can be algebraically manipulated to use L'Hopital's rule. So what is L'Hopital's rule? Well, let's back up a little and recall that sometimes finding limits, you had to use some special algebraic manipulation in order to find the limit. One such example might be something like this. There you have the limit as x goes to infinity of x squared plus 5x over 3x squared plus 4x. And when you put in the infinities here, what you end up with is infinity over infinity. Can't determine what the limit is. You don't know what infinity over infinity is because you don't know the level of infinity on top, level of infinity on the bottom. Maybe this thing goes to 1, maybe it goes to a different number, maybe it goes to infinity, maybe it goes to 0. There's lots of different ways this could go when you have infinity over infinity. So algebraically, what you would do to make this work would be to take the highest power, and in this case it's 2, and then divide every term by x raised to that highest power. So we'll have x squared over x squared plus 5x over x squared all over the 3x squared over x squared, and then plus 4x over x squared. And when you start simplifying the fractions, you end up with a new expression, this 1 plus 5 over x all over 3 plus 4 over x. And then using the fact that a constant over x, when x is going to infinity, will actually just go to 0, you're able to get the answer of 1/3. So that works out really nice. And this type of limit, this infinity over infinity, is known as an indeterminate form. You had to do something before you could actually determine what the answer was for that limit. So here we used algebraic manipulation. Well, now we're going to be able to use derivatives to help find the same limit result of this indeterminate form using L'Hopital's rule. So L'Hopital's rule, one little side note historically, L'Hopital did not develop his own rule. History says that he actually bought the rule from a Bernoulli. And that's kind of an interesting tidbit of history where, basically bought the rights to this theorem. And it's kind of crazy. But at any rate, that's what we call it. That was some money well spent, I guess, because hundreds of years later, we're still calling it L'Hopital's rule. But at any rate, what it says is that suppose that f and g are differentiable and g of x does not equal 0 near a except possibly at a. So what we're going to see here then is that you can suppose that either the limit as x goes to a of f of x equals 0 and the limit as x goes to a of g of x equals 0, or that the limit as x goes to a of f of x equals plus or minus infinity, and the limit as x goes to a of g of x equals plus or minus infinity. And if you have one of these two scenarios, the 0 and 0 or the infinity and infinity, then the limit as x goes to a of f of x over g of x. So note what this is doing for us. It's giving us either 0 over 0 or infinity over infinity. And there could be a plus or minus there with the infinities, but basically you're looking at 0 over 0, infinity over infinity as your two possibilities for L'Hopital's. And what L'Hopital's rule says is that if you want to find the limit of that indeterminate form, you can actually take the derivative of the top, divide it by the derivative of the bottom, find that limit, and you get the same result. And this is not a quotient rule. You're just taking derivative of the top, derivative of the bottom. This is L'Hopital's rule. So you can just take the derivatives and find the limit. Now, if you were to do this up above with this problem, you would still get the 1/3. And I encourage you to pause this video and try it. Take the derivative of the top or the derivative of the bottom. You'll notice you still get an indeterminate form there after the first derivative, but L'Hopital's rule works if you still have an indeterminate form after the first derivatives. So you would just do the derivative of the top again, derivative of the bottom again, and you will see you get the 1/3. I'll let you pause the video and try that on your own. Okay, so a couple of notes here. Based on the rule, the only indeterminate forms that you can use L'Hopital's rule on are the 0 over 0 or infinity over infinity. And again, it could be plus or minus infinity, but basically 0 over 0, infinity over infinity are the only two that L'Hopital's rule will actually work for. And it also works if, and this is something I alluded to with the example up above, but if you get a f prime over g prime and you get that 0 over 0 or infinity over infinity, you can still keep going. You don't have to stop there and say, oh, it's indeterminate after the first derivatives, I'm done. No, you keep going. So basically what this says is that the limit as x goes to infinity, or x goes to a, of f prime of x over g prime of x is going to be equal to the limit as x goes to a of the f double prime of x over g double prime of x, and so on. So basically what L'Hopital's rule allows for is that if you do the first derivative, so top and bottom, you still get an indeterminate form, 0 over 0, infinity over infinity. Well, you can take the second derivatives of the top and bottom, and you just keep doing that until you get to an answer. Okay, so let's see an example here. Let's find the limit. So we got e to the t minus 1 over t cubed. T's going to 0. If you plug in 0 for the t, you get 1 minus 1 over 0, or a 0 over 0 indeterminate form. So let's put L'Hopital's rule into play. So we got this limit as t goes to 0 of e to the t minus 1 over t cubed. And I'm going to take the first derivative of the top, and that's just going to go to e to the t. First derivative of the bottom is 3t squared, and now when I plug in 0, I'm going to get 1 over 0, and that will go to infinity. So this limit is infinity. And that's basically all there is to L'Hopital's rule. You see a 0 over 0, infinity over infinity, start taking derivatives and checking the answers until you get to something. Okay, so let's look at some other indeterminate forms, because as I said, L'Hopital's rule just works for 0 over 0, infinity over infinity scenarios, but there's some other forms that can be manipulated so that L'Hopital's can be used. So one of these forms is the 0 times infinity situation. So in this case, what we're going to use is f of x over 1 over g of x. So basically you're taking the g of x that maybe is producing the infinity or the 0, and you're making it this 1 over g of x. So note here that this is really still, when you think about this 0 times infinity, you're really kind of starting with this form, f of x times g of x, so to speak. So we're going to do f of x divided by 1 over g of x, which is still technically equal to f of x times g of x, but will give us a 0 over 0, or maybe an infinity over infinity result instead of 0 times infinity. Now, doesn't matter what order you do the fraction in, so you could take the g of x, leave that up top, and then divide by 1 over the f of x. And this will get you to a 0 over 0 or infinity over infinity form that you can then use L'Hopital's rule on. So let's go ahead and see this in action. So for this limit here, we got the limit as x goes to infinity of x times sine of pi over x. So the sine of pi over x, if you were to plug in infinity for the x there, you're going to get the sine of 0, which is 0, and the x out front just goes to infinity, so we really have infinity times 0 here. So what we're going to do, and what I'm going to do here is, if I have an algebraic expression versus, in this case, the trig expression, it's a lot easier to make the fraction form with the algebraic part, typically. So I'm going to make this into the limit as x goes to infinity, and then sine of pi over x over 1 over x. So notice if I flip the bottom and multiply, I get back to what I started with. But now in this new adjusted form, what I get up top, I get 0. Sine of 0 is 0. Down below, I get 0. So we're really looking at a 0 over 0 indeterminate form now by making that adjustment. So I can go ahead and use L'Hopital's rule. So I'll take the derivative of the top, and the derivative of the top here is going to be the cosine of pi over x, and then times the derivative of pi over x will be a negative pi over x squared. And then down below, 1 over x will just become a negative 1 over x squared. And if we do a little bit of canceling, you can cancel here. You get the top is just going to be pi cosine of pi over x. And basically what I've done is cancel the top and bottom negative 1 over x squareds. So this really just goes over 1 if I'm going to write it explicitly. Technically, you don't have to. But now let's see what happens when we let x go to infinity. So you get the cosine of pi over x, which will still basically be cosine of 0, which is 1. 1 times pi is pi, divided by 1 is still pi. So we get our answer here of pi. And you're done. So that's one way that you can use L'Hopital's, even if it's not the classic 0 over 0 or infinity over infinity. If you see 0 times infinity, you adjust it. Okay, another form that can be adjusted is this infinity minus infinity. So in this case, there's a few different things you may need to do. You can either get a common denominator, combine the terms, you rationalize the expression, if you have a square root or a root involved, factor out a common factor, but all of those approaches, your goal is to try and get something where it's 0 over 0 or infinity over infinity, which allows you then to use L'Hopital's rule. So let's look at the limit here. As x goes to 0, cosecant of x minus cotangent of x. Well, the cosecant, remember, is like 1 over the sine, so that's basically going to go to infinity when you do 1 over 0. Cotangent, similar thing. It's divided by the sine, so you're going to get infinity out of that. And we get this infinity minus infinity. So in this case, with trig functions, I'm going to adjust these to be in terms of sine and cosine. So you get 1 over the sine of x minus the cosine over the sine of x. And then we can combine these into one fraction. And you get 1 minus the cosine of x over the sine of x. Now, what I'm seeing here is 0 over 0 when I plug in the 0. So I'm going to do L'Hopital's rule, and I'm going to take the derivatives of the top and the bottom, and I end up with a positive sign. The negative sign will go to, negative cosine will go to a negative of a negative sign. So you get positive sign over the cosine. And now with this, you get 0 over 1, which is 0. So you get an answer there after that adjustment. So we'll see the last type in part 2.